Okay, so this is the first of probably two videos on section 6.1, the Laplace transform. This first video, we're going to define the transform, and then we're going to compute some transforms. So what is the Laplace transform? The Laplace transform, denoted by script L. Normally when we draw it, right, it looks like a script L, looks kind of like, it has a few loops in it. We'll see in the next video. Um, and so the input to the Laplace transform is a function of t, and so the Laplace transform is often called an operator because it has a function. Its domain is a set of functions. And so what does the Laplace transform do with f of t? Well, it multiplies it by e to the minus st, and then it integrates that result from 0 to infinity. Couple things to notice here. We're integrating with respect to t from 0 to infinity, so that this is an improper integral, meaning that we have to take the limit as this upper bound goes to infinity. So if you're not sure about L'Hopital's rule, you might take this time to review it. It'll come in handy in a couple of places. And secondly, when we have this e to the s of t here, the s is a parameter that's not touched, right? It's constant with respect to the integral, and if we integrate out the t, then all that's left is a function of s. So therefore the Laplace transform puts in a function of t and outputs a function of s. Good. Just a quick example. Let's take the Laplace transform of e to the at. So by definition, we plug it in, e to the integral from 0 to infinity, e to the minus st, e to the at dt. And I like to rewrite that exponent, bringing them together. I like to take out a negative sign so that the power becomes s minus a times t. And then when we anti-differentiate, right, the e to the something times t, it's 1 over the something times e to the something times t. And so using that, oops, that should be an s minus a there. Sorry about that. So this is going from 0 to infinity. The question is now, does the limit always exist for this quantity as t goes to infinity? And the answer is yes, as long as the s minus a is a positive number, right? And so we want this exponent here to be negative so that the limit then would be 0. And so continuing that on, we end up with just 1 over s minus a. Good. Now, some issues to explore that we'll probably get to in this other video. For what functions f does the Laplace transform exist? You can see that there's some issues here, right? Because number one, the function has to be somehow integrable, and number two, we're integrating out to infinity, so we have to be careful about which functions we do integrate. Recall how to take the limit, like I was just saying, L'Hopital's rule. If you've forgotten that one, go ahead and take a moment to review. And then finally, we should remember how to integrate by parts using a table, because that'll come in handy with these Laplace transforms. Okay. Good. So let's take some more computations here. We showed that the Laplace transform of e to the at is 1 over s minus a. Can you compute the Laplace transform of 1 from this? Well, we can take a to be equal to 0. And so if we do that, we get that the Laplace transform of 1 is 1 over s. Now remember the condition. The condition over here was that s is greater than a. So if this is for a equal to 0, this would only be true for s greater than 0. Okay, so now we've got these two nice Laplace transforms. Let's see if we can take the Laplace transform of just t. And so we compute our integral. And now this is one of those examples, right? We're going to have to integrate by parts using a table. And so let's do that. And so remember, the first column here alternates in sign. The middle column we differentiate, and the outer column we anti-differentiate, right? And so then when we go in and compute the integral, we take the product straight across, so it's going to be plus t times minus 1 over s e to the minus st minus 1 times 1 over s squared e to the minus st, and then plus the integral of the product straight across, but that's just going to be 0. So we're just going to have these two terms, minus t over s e to the minus st minus 1 over s squared e to the minus st. And then we're taking those from 0 to infinity, which is formally, right, the limit as t goes to infinity from 0 to t. And then, so what is the limit as t goes to infinity of this stuff? Well, this second term here, the e to the minus st, we've already dealt with. How about t e to the minus st? This is where we could use L'Hopital's rule to show us that this limit is 0, and I'm going to leave that as an exercise for you. That's on our worksheet. And so assuming then that we can compute this limit to be 0, then we evaluate at 0. So notice that this first term then would 0 out, and the second term would be minus 1 over s squared, which is 1 over s squared. So altogether then, the Laplace transform of t is 1 over s squared. Now we're starting to get quite a few Laplace transforms, and so what ends up happening is we end up having, let's do one more first. Sorry about that. Let's use the Laplace transform of the exponential to compute the Laplace transform of cosine and sine. So how are we going to do that? You can probably guess. We're going to complexify the problem. So we're going to take the Laplace transform of cosine of at plus I sine of at. Right, so cosine of at plus I sine of at is e to the iat. And what is the Laplace transform of e to the iat? So just using our previous formula, it's 1 over s minus ia, right? And so if I multiply top and bottom by the conjugate, I get the result s plus ia on the top over s squared plus a squared on the bottom. So remember, we're treating this as a real number here, right? Okay, and so now you can see what the Laplace transform of the cosine is. It's the real part of this expression, and the Laplace transform of the sine is the imaginary part of this expression. So just being explicit about that. Beautiful. So it goes fast. Notice that if you were to use the definition, right, you would be integrating e to the minus st cosine of at, which requires integration by parts twice, right? That takes a long time to compute. So this is just a fast way of computing it if you happen to forget and you don't have a table. What table, you might be saying to yourself? Well, there's this table. So for exams, you're going to be given this table. It's a little bit different than the book. The nice thing here is that we're listing all the different formulas for each of the sections that we're going to be looking at in chapter 6. So you can see that we've gotten through the Laplace transform of 1, e to the at. We haven't done t to the n yet, but you might double check the formula here. We just did t to the 1 power. So here's the formula for t to the n. Sine of at, cosine of at, we've proven now. And so I believe that's it. So this is computing Laplace transforms. In the next video, we will be looking at a little bit of theory, and then we'll come back to this table for some computations. Okay, I'll stop there.